Imagine you're trying to figure out where a friend is standing in a dark room. You can't see them directly, but you know they're always between two other people, and those two people are walking toward the same spot. Your friend must end up there too. That's the squeeze theorem. Here's the formal idea. Suppose you have three functions, g of x, f of x, and h of x, where g of x is less than or equal to f of x, which is less than or equal to h of x, for all x near some point a. If the limit of g of x as x approaches a equals L, and the limit of h of x as x approaches a also equals L, then the limit of f of x as x approaches a must also equal L. Why does this work? Think about epsilon, any tiny positive number. Since both bounds approach L, there's a neighborhood around a where g of x and h of x are both within epsilon of L. But f of x is trapped between them. So f of x must also be within epsilon of L. Since this works for every epsilon, no matter how small, the limit of f of x is exactly L. The classic example is the limit of sine of x over x as x approaches 0. You can't just plug in 0. But using geometry of the unit circle, you can show that cosine of x is less than or equal to sine of x over x, which is less than or equal to 1. As x approaches 0, cosine of x approaches 1, and the upper bound is already 1. Squeezed between two values that both approach 1, sine of x over x must also approach 1. Here's another example. What's the limit of x squared times cosine of 1 over x as x approaches 0? Cosine of 1 over x oscillates wildly, but it's always between negative 1 and 1. So the whole expression is squeezed between negative x squared and x squared. Both approach 0, so the limit is 0. This theorem is powerful precisely because it handles functions that are too erratic or complex to evaluate directly. Sometimes the smartest move isn't solving the problem head-on. It's trapping the answer between two simpler things you already understand.